Welcome back. So far we have seen the that number of spectral line, and somehow we have finished the instrumentation. Okay, but the instrumentation which will be we have seen the detailed instrumentation of ESR, but for exam perspective we will see the only the block diagram for the ESR and how it actually works. Okay, so for exam perspective these things are necessary. So question might be asked in such a way that with block diagram explain the ESR spectrometer. Okay. With block diagram explain the ESR spectrometer. So here we need to draw just the this given block diagram. Okay. So we need to draw the given block diagram. So in that block diagram we have been shown with the this whole thing is nothing but the wave meter. In that we are having the various parts, okay, or various components. One is the klystron, one is the klystron source. Okay, I think all of these things are already seen in the previous videos. Then another one is the wave meter or the wave guide is there. Another one thing is the attenuator, isolator is there. Then sample cavity is also there. So in that whole thing, that isolator, wave meter or the sample cavity, we are having the all things. Okay, and one important part is the magic T. Okay, then next is the various detectors are there. Okay, crystal detectors. And another one is the important thing is the magnetic system, how it is useful for the changing the magnetic field. Then next is the uh, our modulation coils, and last one is the recorder and the display units. Okay, so these are the certain components of the ESR. So we'll see the each component one by one. Okay, so important is the klystron, magic T, our sample cavity, then magnetic supply, detectors. Okay, so these are the certain important components of the ESR spectrometer. So the ESR spectrometer, which consisting of various components. So out of this various component, the first component is the source. Okay, and the in the source we are specifically seeing the klystron source. Okay, klystron. So most of the ESR spectrophotometer having the source as a klystron oscillator, which is operating in the microwave region. Okay, and we have seen that this ESR spectrum is work under the microwave region in the frequency of around 9 to 10 gigahertz. The vacuum tube, generally this klystron source is nothing but the vacuum tube which will produces the microwave radiations centered on a very small range of frequency. Okay, so 9 to 10 gigahertz frequency is generally given as a microwave region. Okay, and the frequency of monochromatic radiations are determined by the voltage which is applied to the this klystron source. Okay, and generally 300 milliwatt power source is used for the generation of microwave radiation. Okay, so the klystron tube which is acts as the source of radiation, it would stabilize the temperature fluctuation by immersing this coil into or this tube into the oil bath or by the forced air cooling. Okay, so certain heating will takes place, so that heating can be eliminated by this immersing this tube into the oil bath or by certain air cooling. Okay, the frequency of monochromatic radiations is determined by the voltage which is applied to the klystron source, and it is generally kept at a fixed frequency by automatically controlled circuit, and it will provide the power output of around 300 milliwatts. Okay, so these are the certain important points for the klystron source. Okay, so the next component is the isolator. Okay, so the main function of isolator is the it is a non-reciprocal device which would minimize the vibration in the frequency of microwave produced by the klystron oscillator. Okay, So isolator will gives you the very narrow band of frequencies which will be necessary for the analysis of samples. Okay, so it will eliminate the higher as well as lower frequency waves from the desired frequency range. Okay, so it is a device which will minimize the vibrations in the frequency of a microwave produced by the klystron oscillator. The oscillators which are generally used to prevent the reflection of microwave power back into the radiation source. So it is a strip of ferrite material which will allows the microwave in one direction only, and also it will stabilize the frequencies produced by the klystron. Okay, so the main function of this isolator is the main function of isolator is the like to minimize the fluctuation in the frequencies in the microwave region, and generally it is a ferrite component. Okay, ferrite material which will cause the or minimize the fluctuation. Okay, so next part is the wave meter. So as the name is suggesting, wave meter is used to measure the frequency produced by the klystron oscillator. Okay, wave meter will measure the frequency produced by the klystron oscillator. It is put in between the oscillator and the attenuator. Okay, the wave meter is placed between the oscillator, that is our source, and the attenuator. Okay, and so to know the frequency of microwave produced by the klystron oscillator, the wave meter, which is nothing but also called as a wave guide. Okay, the wave meter also called as a wave guide. So the wave meter, which is generally calibrated in the frequency units of megahertz instead of wavelength. Okay, and the waveguide, which is nothing but a hollow rectangular brass tube, it is used to convey the wave radiation to the sample and the crystal. Okay, now certain important, okay, source component is one another important component is the, okay, attenuator. Okay, it is not mentioned here, but the important component is the attenuator. The power propagated down through the waveguide or the wave meter, which may be continuously decreased by inserting a piece of a resistive material into the waveguide. This piece is also called as a attenuator or variable attenuator. So it is used to vary the power of sample from a full power of klystron to one attenuated by the force of 100 or more. Okay, so if you want to like decrease the energy of the radiation produced from the klystron source, then we will insert certain resistive material plates or piece of the resistive materials into this wave meter or the wave guide, so that the power of our full power of klystron source is attenuated or altered by the force of around 100 or more. Okay, so these are the certain important components of the source. Okay, so in the source we have seen the first is the klystron, the second one is the isolator, wave meter or the wave guide, and one another component is the our attenuator. Okay, attenuator. Now next component is the circulator or the magic T. Okay, so as the diagram is showing, okay, here circulator or the magic T is consisting of the four arm, and how that arm are actually working, that we can see in the working section. But for our instrumentation purpose, the circulator or the magic T is nothing but the microwave radiations which are produced by the source or klystron source are oscillated and then are allowed to pass through the oscillator wave meter, and they will finally enter into the that circulator through the waveguide. Okay, so the path of this radiation will be from source to the our isolator, then into the wave meter. Okay, and in between wave meter we can have the attenuator. So once that waveguide, generally made up of or of the rectangular copper or the glass tube, which is to be having the silver or gold plating inside, so as to produce the very high conducting flat surface, and the microwave radiations which are enters through the one arm, that is arm 2, is connected to the resonance cavity of a sample arm 3. So this general output is given out in the form of arm 4. Okay, so radiations are entered into the arm 2 and 3, and output is given in the arm 4. Okay, so that is the magic T. Next component is the sample cell or the sample cavity. The heart of ESR spectroscopy or ESR spectrometer is nothing but the sample cavity containing the sample. Okay, the cavity system is constructed in a such a way that it would maximizes the applied magnetic field along the sample direction. The sample value, which is having the around 0.50 to zero point 0.5, this 0.50 is the size of the cavity and 0.5 ml is the amount of sample ml required in the ml. Okay, which can be used with the sample which does not possesses the dielectric constant. So while for the high dielectric constant material, the sample cell should having the thickness of around 0.25 millimeter and the sample volume required is the 0.05 ml. Okay, so for depending upon the dielectric constant of the sample, the sample cavity or the sample cell changes its characteristic properties. Okay, the electromagnetic material which provides the homogeneous magnetic field which can be varied from the 0 to 500 grams. Okay, oh, 500 gauss. Okay, so the magnetic field is varied from 0 to 500 gauss. Okay, and also this sample cavity are nothing but the rectangular cavity and cylindrical cavity based upon the our application. The most of the ESR spectrometer having the dual sample cavities which are generally used, and this is done for the simultaneous observation sample and the reference material. Okay, and the reference material which is used in the this ESR is the DPPH. Okay, since the magnetic field interacting with the sample so as to cause the electron spin resonance, the sample is place where the intensity of the magnetic field is greatest. Okay, so we need to place the sample cell or sample cavity near that area where the we are having the maximum where we are having the maximum magnetic field. So here we can see that the sample cavity is generally placed in the magnetic field. Okay, and one component, that is arm 2 of the our magic T, is interacting with the sample, and once that interaction has been takes place, we get the output of our ESR spectrum. Okay, ESR spectrum. So this is the sample cavity. Then next is the crystal detectors. Crystal detector is nothing but the most commonly used crystal detector is the silicon crystal detector, which will convert the radiation into the DC. Okay, DC, that is direct current from the microwave radiation. So output is coming in the form of a direct current which will be measured by using the silicon detectors. Okay, also there is an important component, that is the magnetic system. So the resonant cavity or the sample cavity is placed between the poles of the electromagnet. The field which should be produced, that is the magnetic field, should be stable, and it should be uniform over the sample volume. The stability of field should be achieved by energizing the magnet with the very high regulated power supply. So these are the certain important thing that we need to consider for the um, while considering the our magnetic system. The ESR spectrum, which is recorded by slowly varying the magnetic field through the resonance condense coil by sweeping the current supplied to the magnetic field by the power supply. Okay, so magnetic field or magnetic component is also important for measuring the ESR spectrum, because once we are going to incident the certain amount of frequency, then we will generally vary the magnetic field and we measure the ESR spectrum. So the last component is the display device. So once we have got the system, or the signal in the form of DC current by converting the microwave radiation from the silicon detector into the DC current. In order to observe this signal, the signal system is connected with the display devices, okay, various display devices. So this is the instrumentation for the ESR spectrum or ESR spectrometer. Okay, so the important component are the klystron, isolator, attenuator, wave meter or waveguide, then sample cavity, okay, then magnetic field, okay, magnetic field. The next is the detectors, and last one is the display devices. So if the instrumentation is asked, you need to draw the block diagram for the ESR spectrometer. Then you need to explain the each and every component in brief. Okay, so how that actual working of the ESR spectrum or spectrometer will occur, we'll see that in the next lecture.